This is a problem that Isaac Newton himself was stuck on. It's commonly known as the three-body problem, and it's infamous for its inability to be solved for the past few centuries. In fact, the nature of this problem is inherently chaotic, meaning that it is practically impossible to predict the conditions of any object in this three-body system at any given point in time. And furthermore, a tiny change, and I mean an extremely small change in the positions, velocities, or any initial conditions of the system results in a completely different trajectory for the system in the future. I'm sure some of you are asking yourselves, but why exactly is it impossible to solve? I might have heard of this problem, but I've never understood why exactly it was so hard to solve, even for someone as brilliant as Isaac Newton. As always, it's usually easier to start from a simpler version of the problem to see what's going on. So let's start from a case that is possible to solve. A system where there are only two bodies that exert gravity on each other. An example of this kind of two-body problem, I'm sure you're all familiar with. Take the Sun and the Earth, for example. Because of the gravitational forces that the Sun and the Earth exert on each other, this familiar orbit is created. So what we'll do is we'll draw what's called a free body diagram, which is basically just drawing out all the forces in a system. So as you can see, the Earth and the Sun each pull each other with some gravitational force. And this is, of course, a force that I'm sure you're all familiar with, and it creates the path of the Earth's orbit, which it revolves around once every 365.25 days. So let's say that the Earth and the Sun start in these positions. How exactly do we figure out their subsequent positions and velocities at any given point in the future? There's a lot of complex math that goes into this, but the gist of it is this. You can split the entire two-body problem into two separate one-body problems that can each be solved. You do this by starting with Newton's second law, which I'm sure you're all familiar with. It's just F equals ma. In this case, though, there's two versions of this equation, one for each of the two bodies involved. So F1 equals m1 times a1, and F2 equals m2 a2. Now, since F1 and F2 by Newton's third law are equal and opposite to each other, F1 plus F2 has to equal 0. And if we treat the two separate bodies as a single center of mass, if you will, which I'll just call R, the force on that center of mass is the sum of the masses, or m1 plus m2, times the acceleration of that point, which is AR. Now, since that also has to equal 0, since the sum of the forces is 0, that means the acceleration of R has to equal 0. And if the acceleration of R is 0, the velocity of R has to be constant. So now you can determine the position of R from the initial conditions with respect to time, because the velocity is constant. So the second one-body problem involves an algebraic manipulation of the two original F equals ma equations. And you can see this on screen. You get a1 minus a2 equals f1 times 1 over m1 plus 1 over m2. And we can just replace, for simplicity, a1 minus a2 with a new variable. I'm just going to say a of small u, just to make it easier to see. So if you do some manipulation on this equation, you get f equals au times m1 m2 by m1 plus m2. So now you also have the function of f with respect to u. So now that you can know the position of the center of mass and the force, you can use these variables to solve the entire problem. If you want a more rigorous proof, I'll just link it in the description because I glossed over a lot of details here and skipped some steps. Because we were able to represent all the unknowns with different free equations of motion, we can create a model that can accurately represent the two-body problem. And this holds true no matter what two bodies you start with, where you start them with, at what time, what distance, it doesn't matter. And this is a completely non-chaotic system. But now, let's get into the heart of the three-body problem. What changes about the system simply by adding a third body? In this situation though, it's just much more complex. Each body has not just one force acting on it, but two, from two separate bodies. There's 3 masses and 3 positions to account for, and way too many equations of motion. In fact, you need 9 second-order differential equations to fully account for the variables in this system, which makes it pretty much generally impossible to solve. If you want, we could try the same attempt of using Newton's second law to form equations representing all of our unknown variables. Using the common method of the gravitational equations of motion, we get a set of 3 equations, as can be seen on screen here. But as you can kind of see, the difference over here is kind of evident compared to the 2-body problem. There's just way too many variables to deal with. Previously, we were able to use the trick of finding a common center of gravity, which allowed us to represent all the variables with different equations of motion. But if you were to try this out, you would see that a center of mass doesn't really solve this problem. And you can try countless tricks, and mathematicians definitely have. But overall, there's no way to create a set of closed-form equations. In other words, we cannot solve this problem analytically. So if hundreds of mathematicians and physicists from around the world have tried this problem and failed to come up with a general solution, does this truly mean that we will never be able to ever solve this problem? Well, not quite. You may notice that we have been using the word general quite often when referring to a solution to the 3-body problem. This is because more specific solutions do exist in some cases. So here's a bunch of known special solutions to the 3-body problem. Many of them, most of them, form beautiful patterns and are periodic in nature. For example, take the figure-8 solution. The bodies, if they have variables within a certain range, are periodic, and so the forces act just right to make the system keep repeating itself over and over, making it predictable. Further on, this unsolvability that we mentioned is largely due to the constraints of the problem itself. You may have noticed that we mentioned closed-form solutions to the problem. This refers to a solution that can be analytically solved through basic equations. But this doesn't really mean that the solution cannot be found at all. In fact, there was a mathematician by the name of Sundman who created a converging series based on some truly complex math, which manages to provide solutions for the given problem in a lot of instances. The only issue is that for this converging series to eventually converge to a value that, would give us a decent range of accuracy, it takes an insane number of terms, like way too many to be solved by hand or even by a computer. So for example, just to be used for our everyday astronomical observations, it's estimated that it would take 10 to the power 8 million terms, which is 1 followed by 8 million zeros, which is just, we're never going to touch that number in any way, shape, or form. So this solution by Sundman, even though it could work theoretically, is just insanely impractical to us compared to the alternative of doing a discrete simulation. And this was just 3 bodies. And of course, many cosmic systems have many more bodies. The more general name for this problem is the n-body problem, where n just means any integer you can possibly think of. Our solar system, for example, is roughly a 1 million body problem given all the asteroids and comets and moons and other things that we just forget to think about. So the system we're showing on screen here is a much simpler system than the million-body system it actually is, but it's still an intricately complex problem, again, resulting in chaos and basically making it impossible of finding solutions. Although there's a part of me that's quite sad we'll never be able to perfectly solve any of these n-body systems, the intricacy that comes from them is what makes them quite beautiful to look at.